Okay, we're going to be moving on to Chapter 2, which is our first exposure to describing motion in this chapter. It's titled One-Dimensional Kinematics. Kinematics is the study of motion. We'll just be thinking about objects either moving along the x-axis or moving along the y-axis. We're going to discuss in this video position, distance, and displacement, and average speed and average velocity, and distinguish between those and instantaneous velocity. So when you start to describe the motion of something, you have to have some kind of reference point. You have to know, like if something's moving, you need to be able to describe which way it's moving. So it's important for you to be able to describe the initial position of an object and the final position of an object. So you have to have a reference point so that you can define a direction of some kind of coordinate system. Distance is simply just the total length that you've traveled. So if you drive from your house to the grocery store and back, you travel 4.3 miles one way and 4.3 miles the other way. And that's a total of 8.6 miles. But that is a quantity that has no reference to direction at all, just how far you've traveled. It's a scalar quantity in its distance. Displacement, though, is different. It's your change in position. If you drove from your house to the grocery store, so you went 4.3 miles in the direction of the grocery store, and then you turned and you went all the way to your friend's house, you traveled backwards 4.3 miles as you passed your house, and then you continued traveling even further, and you ended up 2.1 miles behind your house. But the total distance that you traveled was 10.7 miles. So your displacement is your change in position, and that's when that reference comes into place, right? You have to know where your start point is, and you have to know what your coordinate system is. Which way is positive, which way is negative. Displacement is a vector quantity. When we talk about finding the average speed of our trip, imagine going to the beach. Maybe the beach is 150 miles away, and you know it's going to take you about 3 hours. So 150 miles divided by 3 hours is the total distance divided by the total time to go on the trip. And that distance divided by the elapsed time is referred to as the average speed. We don't really care what direction we're going in or anything like that. That's all we want to know. So in this problem here, we have a car that's traveling at 30 miles per hour for 4 miles and 50 miles per hour for 4 miles. So what's its average speed? Would you just add these up and divide them? Or would you have to do something different? Well, it turns out that what you would have to do is find the total distance that it traveled and divide it by the total time that it traveled. The total distance is first going to be found, the total time first has to be found. The total distance is easy, it's 8 miles. But he drove at a different speed in each case. So what I'm going to do is I'm going to take 4 miles and I'm going to divide it by 30 miles per hour. That's going to give me a time of 0.133 hours. If I take and do the same thing for the second part of the trip, 4 miles divided by 5.0 miles per hour, I'm going to get 0.08 hours. If I add those together, I get a total of 0.213 hours. So 8 divided by the total time is going to give me a speed of around 37.5 miles per hour, which is lower than what you would think, right? It's lower. Average velocity is a little bit different. It's a vector quantity, and it does have to do with the change in position, not the distance. So it would be your displacement over your elapsed time. So imagine this runner is running from the 0 mark, 50 meters, and then back. The total distance that he traveled would be 50 plus 50, or 100 meters, but his total displacement would be 0. So he has a different average velocity than he would have an average speed. When we graph motion, we usually graph three different types of graphs: a position time, a velocity time, or an acceleration time. So what we're going to do here is we're going to look at this object. At t equals 0, traveled 3 meters, and at 1 second he traveled another meter, and at 2 seconds he traveled another meter, and he stops and he turns around and he goes backwards. So we actually plot that motion and we talk about what that graph looks like. Notice that during the very first second he traveled roughly at the same rate, right? He traveled about the same distance every instant in time. It's pretty linear. But then, as he started to slow down, it starts to curve and become flat. And notice that this slope at this very instant is 0, right? He stops at that instant, and then he starts to go backwards. And notice that the slope is now becoming constant again, right? But it's a negative slope. So the slope of this graph is giving us the velocity of the object. But let's look back at that one more time. If I wanted to find the slope at any instant, right, then it would, excuse me, then that would be the velocity at any instant in time. For instance, at 2 seconds he stopped, and the slope at that instant is a 0. That is called the instantaneous velocity. Whereas when we find the slope between any two points on the graph, that's the average velocity, because that would be the displacement over the time. The slope at one instant, or the slope of the line tangent to the curve at that instant, is the instantaneous velocity. When you look at your speedometer, you don't get a measure of your average velocity. You get the velocity at that instant in time. And it's not really even velocity, right? Velocity has a direction associated with it because it's a vector. It's called a speedometer because it's giving you instantaneous speed at that instant. So the slope of a line tangent on a position graph is the velocity at that instant, the instantaneous velocity. But the slope between 2 points is the average velocity on a position graph. So when we graph motion, right, a position graph for something that's traveling at a constant velocity, you're traveling at a constant velocity, you're going to change your position by the same amount every instant in time. So if you look at this position time graph, the slope of that position time graph is constant, and the slope of it is positive, so this object would be moving in a positive direction every instant in time at the exact same speed. If we graph the velocity, it plots as a positive velocity, and it's not getting any faster or slower, so it has 0 acceleration on the acceleration graph. But contrast that to the constant acceleration graphs. The position time graph is going to be parabolic for something that is undergoing constant acceleration, because the slope is changing by the same amount every instant in time. When I plot that slope every instant in time, because it's changing by the same amount, it's rising by the same amount every instant in time, the velocity graph is linear, and the acceleration graph will be a flat line on whatever the slope is of the velocity graph. And that concludes our discussion of speed and velocity.